Welcome to this video on the Standard Model as a gauge theory. Today, we'll explore how symmetry principles form the backbone of our understanding of fundamental particles and their interactions. So, what exactly is a gauge theory? At its heart, a gauge theory is a type of field theory where the Lagrangian, which describes the dynamics of a system, is invariant under certain local transformations. This invariance is called gauge invariance. A local transformation means that the transformation can be different at every point in spacetime. Gauge invariance means that the physics described by the theory remains the same even if you perform these local transformations. The requirement of gauge invariance is a powerful constraint that dictates the form of the interactions between particles. It necessitates the existence of force-carrying particles called gauge bosons. These bosons mediate the fundamental forces. Let's visualize what a symmetry transformation means. Consider a simple object, like a circle. If we rotate it, it looks exactly the same. This is a global symmetry. In a gauge theory, we have local symmetries, transformations that can vary from point to point. Think of this as allowing different parts of our system to rotate by different amounts, yet the physics remains unchanged. In quantum mechanics, a common gauge transformation is a phased transformation of the wave function. This can be different at each point in space and time, yet the probability density remains the same. The Standard Model is a gauge theory based on the following symmetry group: SU3C times SU2L times U1. Why this mathematical expression might look intimidating, but we can break it down into its components to understand what each part represents. Let's start with SU3C. The SU3 stands for Special Unitary Group of Degree 3. In mathematical terms, it's a group of 3 by 3 unitary matrices with determinant 1. The subscript C stands for color. This refers to the color charge of quarks, which come in 3 types: red, green, and blue. This is just a naming convention. Quarks don't actually have colors in the visual sense. This part of the Standard Model describes the strong force, which binds quarks together to form protons, neutrons, and other hadrons. The gauge bosons associated with SU3C are the gluons. There are 8 different gluons that mediate the strong force. Gluons carry color charge themselves, which leads to unique properties of the strong force, like confinement. Next, let's look at SU2L. The SU2 stands for Special Unitary Group of Degree 2. Mathematically, it's a group of 2 by 2 unitary matrices with determinant 1. The subscript L stands for left-handed. This is because the weak force acts only on left-handed fermions and right-handed antifermions. This is a profound asymmetry in nature. This part of the Standard Model describes the weak force, which is responsible for radioactive decay and certain types of particle interactions. The gauge bosons associated with SU2L are the W+, W-, and Z0 bosons. The W bosons carry electric charge, while the Z boson is neutral. These bosons are massive, which gives the weak force its short range. Finally, let's discuss U1Y. The U1 stands for Unitary Group of Degree 1. Mathematically, it's the group of complex numbers with absolute value 1, or equivalently, the group of rotations in a 2D plane. The subscript Y stands for weak hypercharge. This is a quantum number related to both electric charge and weak isospin. This part of the Standard Model, together with SU2L, describes the electroweak force, which unifies the electromagnetic and weak forces at high energies. The gauge boson associated with U1Y is the B boson. However, the physical photon and Z boson are actually mixtures of the B boson and one of the SU2L gauge bosons, as we'll see when we discuss electroweak symmetry breaking. One of the most profound aspects of the Standard Model is electroweak symmetry breaking. At high energies, the electromagnetic and weak forces are unified as a single electroweak force with the symmetry group Su 2L times U1Y. However, at lower energies, this symmetry is broken by the Higgs mechanism. The Higgs field, a scalar field, has a non-zero vacuum expectation value. This breaks the Su2L times U1Y symmetry down to U1EM, which is the gauge symmetry of electromagnetism. Through this symmetry breaking, the W+, W-, and Z0 bosons acquire mass through their interaction with the Higgs field. The photon, on the other hand, remains massless because it doesn't couple to the Higgs field in the same way. This mechanism is also responsible for giving mass to the fermions, the quarks and leptons, through Yukawa interactions with the Higgs field. Let's summarize what we've learned about the Standard Model as a gauge theory. The Standard Model is based on the gauge symmetry group Su3c times Su2L times U1Y. Su3c describes the strong force mediated by gluons, which bind quarks together. Su2L times U1Y describes the electroweak force, which at low energies breaks into the weak force mediated by the massive W and Z bosons, and the electromagnetic force mediated by the massless photon. The Higgs mechanism explains how this symmetry breaking occurs and how particles acquire mass. The Standard Model's success lies in its ability to unify 3 of the 4 fundamental forces under a single mathematical framework based on gauge symmetry. It has made numerous successful predictions and remains one of the most well-tested theories in physics. However, it doesn't include gravity and has other limitations, pointing to the need for physics beyond the Standard Model. The search for a more complete theory continues, but the gauge theory framework of the Standard Model will likely remain a cornerstone of our understanding of the universe.